Okay. So we are going to continue and actually write the proofs today for mathematical induction. Okay? So this is what you wrote down yesterday. Remember, we're going to be given a statement, P7 equals sum. Okay? And what we're going to do is we're going to show it's true for 1. And then for every, we're going to plug K in and say, okay, if P sub K is true, then let's use some algebra and show that that makes K plus 1 true. And if we can do that, then we can say that this is true for all positive integers. Okay, and that's what we talked about forever yesterday. Right? We had the domino example, all of that. Okay. So this is how we're going to break it down today. Okay. First of all, we're going to verify the formula is true when n equals 1. So you're going to actually write 1. And you're going to plug in 1, and you're going to make like a little check mark. Yes, it worked out. Then we're going to assume the formula is true when n equals k. Okay, so you're actually going to write the word assume. Basically, you're just going to plug in k. You're going to write the word assume, plug in k.
The word assume.
Word assume. Okay, and then we're going to show with our algebra that k plus 1 is true. And if that works out, then we can say it's all true. Okay? So we have to assume it to write the proof. Okay? So then, we're going to show that the formula S sub k plus 1 is true. And when we say it's true, that's where the P sub k plus 1 is coming in. Okay, that work that we did yesterday. Okay. So we're going to show that the sum of the k plus 1 number of terms is true. Okay. Now, I want you to think about the sum of the first k terms. Okay, you plug in 1, you plug in 2, you plug in 3, you plug in 4, all the way up to k, right? If we're talking about the sum of the first k plus 1 terms, we plug in 1, we plug in 2, we plug in 3, we plug in 4, we plug in k, and we add the k plus 1 term. Okay? So we're going to have a sum and then of the first k terms. To get the sum of the first k plus 1 terms, we're going to have to add that k plus 1 term. And we kind of saw that yesterday, but I'll show you what I mean when we get to our actual example. Okay? I know a lot of you are like, what are these p's and s's? Okay. Once we do the two examples together, you're going to look back at these s's and p's, and they're going to make a little bit more sense. Okay? That's usually how it goes, right? Okay. So, the first formula that we are going to prove is this. So go ahead and write it down. S of n equals 1 plus 3 plus 5 plus 7 all the way up to 2n minus 1 equals n squared. What is our first step? Verify it is true when n equals 1. So, the sum of the first term is, what's the sum of the first term? 1. And what happens when we plug in 1? Does 1 equal 1 squared?
Yes.
Okay, we have verified that it's true for n is 1. Well, like, so this s sub 1 means the sum of the first term, which is this. If this was s sub 3, if this was s sub 3, it would be 1 plus 3 plus 5. Okay, so we verify that it's true for the first. Okay, now, in the second part of our proof, we are going to assume that it is true for k. So we're going to assume that s of k is 1 plus 3 plus 5 plus 7 all the way up to 2k minus 1, and that's going to equal k squared. So we assume it is true for k. So now we're going to work with our k plus 1 sum. Okay. So if s sub k is 1 plus 3 plus 5 plus 7 all the way up to 2k minus 1, then the sum of our k plus 1 terms would be 1 plus 3 plus 5 plus k plus our k term plus our k plus 1 term. If I'm adding up, okay, so this is the sum of the first k terms. So if I'm finding the sum of the first k plus 1 terms, I add up all of the terms to k and then add the k plus 1 term. Does that make sense? Why that is? Okay, let's think of numbers. If I'm taking the sum of the first 5 terms, I can get a value, right? If I'm finding the sum of the first 6 terms, I would take the sum of the first 5 and add the 6th one.
So always ask you for like one more, then we'll do it.
Well, yeah, that's the goal right here, is that, okay, we start with assuming it's true for k. Now we're going to look at what k plus 1 looks like. Okay, so I wrote the sum. This is the sum of the first k terms, and then I added the k plus 1 term.
I understand.
Okay. Any other questions before I move on? Okay. Now, we're not going to write what this equals. We need to show that this equals what? This is where your practice comes in from yesterday. If s of k is k squared, what do we need to show s of k plus 1 equals? Exactly. Okay, so I'm going to write that right here. If I can show that the sum of the first k plus 1 terms is k plus 1 squared, then our proof is done. Okay, so I wrote the sum, and then I plugged k plus 1 into here. It doesn't equal it yet. Write it at the bottom of your page, or a few lines down. Okay, because now we're going to do algebra to get from here to here. Okay, but I think it's important that you write that down at the bottom of your proof so you know that when you get to that, you are done. You know what you are working towards. Okay, so now let's write this to look a little bit better. We have 1 plus 3 plus 5 plus 7 plus 2k minus 1 plus, what is this?
2K.
Careful. Plus 1. Okay, always plug in with those parentheses. Okay. Well, now, this is what I want you to notice. Here I have 1 plus 3 plus 5 plus 7 all the way up to plus 2k minus 1. Do you see that anywhere else? Ah, this 1 plus 3 plus 5 plus 7 all the way up to 2k minus 1, we have assumed that it equals k squared. So what can we do with this big long sum? Okay, so we can say that 1 plus 3 plus 5 plus 7 plus blah 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 to 2k minus 1 equals k squared. And then we have plus 2k plus 1. Okay, now we want to work towards k plus 1, the quantity squared. Do you think we can do that? By doing what? Factoring. K squared plus 2k plus 1 is k plus 1 times k plus 1. So we have now shown with our algebra that s of k plus 1 indeed equals k plus 1 squared. So since we showed it was true for 1, we showed that the k sum implied the k plus 1 sum was true. So to conclude, remember we're kind of writing a math paragraph, if you will, okay? What did we just do? We just showed that our sum is true. And what was our sum? 1 plus 3 plus 5 plus 7 all the way up to 2n minus 1 really equals n squared. We showed that this is true for all positive integers n. Basically, this is saying if you want the sum of the first 5 odd numbers, then take 5 squared, and that's what it is. If you want the sum of the first 8 odd numbers, take 8 squared, and that's what this one. Okay. So we just showed that that is true. Okay. Questions on this example? Really, as long as you can remember the structure and the order in which things need to be written, the only thing that you really have to do is some algebra in between. And like basic algebra, like algebra 1 algebra. Okay? The biggest pre-calculus thing that we're doing here is just remembering the process. Okay? Yeah.
So, can you just automatically like switch in for k?
Yes. Kind of like our domino. Okay, we have n dominoes. Well, let's show that any given domino is going to knock over the next one. That's kind of what we're doing by using the k and k plus 1. Would you like to see another example? I would love to, Mrs. Hillman. I would love to. Okay. So let's write our proof. Step number 1. Okay, we need to show it's true for what? So the sum of our first term is 5. And n is 1. So we have 1 times 1 plus 4. 5 equals 5. Okay. Second step, what's the word we need to use? Assume. Assume what? Okay. Take your entire sum, replace all of the n's with k's, including this p over here. So k times k plus 4. I kind of got it squeezed in there. Sorry. Now let's think about the k plus 1 sum. We don't know what it equals, but we know we're adding up 5 plus 7 plus 9 plus 3 plus 2k. And then what do we do? We add what term? What term are we adding?
K plus 1.
The k plus 1 term. Okay. If I'm summing up the k plus 1 sum, I'm adding up the first k plus 1 terms. Okay. Now, we don't know what this equals, but we want to show that it equals what?
K plus 1 multiplied by k plus 1 plus 4.
So, times k plus 5. Okay. So, our k plus 1 sum, let's make it look a little nicer for that last term, is 5 plus 7 plus 9 plus 3 plus 2k plus, what does this become?
5 plus 2.
That's what this is right here. Because we have to add up all of the terms leading up to k plus 1. So that has to include the k term. Okay. Now, what do we know about that I highlighted in red? We assumed that it was
K, kids.
okay. We assumed that the sum of the first k terms is k times k plus 4. Okay. So what are we going to have to do with this in order to get to something that looks like this?
We have to combine common factors for the k plus k4. Like
Distribute.
Yep.
Let's call it distributing. Okay. So k squared plus 4k plus 5 plus 2k. Which, combining like terms, is k squared plus, can't add this morning, plus 6k plus 5. Now, does that factor to k plus 1 times k plus 5? It sure does.
We
Okay.
don't have ones that aren't true.
I will not give you one that is not true. Yes.
How come we have to change the variable to k instead of leaving it as n?
Because K is kind of like we're choosing a particular value, and we have to show that that particular value makes the next one true, so that 1 makes 2 true, 2 makes 3 true, that kind of thing. So then, once we can say that, then it's true for any n. Okay, so saying K is like kind of like kicking the domino, so that it's going to knock over the next one. Does that make sense?
Yeah.
Okay. Amanda?
Oh, I'm still confused if we're using the k plus 1 and k plus 5.
Okay, up here, the sum of our first k terms is k times k plus 4. So we need to show that the sum of the k plus 1 terms is k plus 1 times k plus 1 plus 4. Okay, that's what we practiced yesterday, right? Now this is just where it's going in the proof. Okay? This is k times k plus 4. Okay. So now that we finished our proof, you need to write a conclusion. Therefore, S of n is true for all positive integers n. Yes. Okay? Your algebra is the meat and potatoes of the proof. Okay? You have to show step by step by step by step. Okay? You cannot jump from k squared plus 4k plus 5 plus 2k to this factoring. Because you wouldn't do that if you didn't know what it factored to. Okay? So, you better make me believe that you know what you're doing with your algebra. You can't skip steps. Okay? Because your algebra is the proof. Okay? Now, we have time left in class on purpose. You have 5 problems. My goal for you right now is to work on 2 of these. And then you can have 3 of them for your homework. I want to be here with you while you're writing 2 of them, so that I know before you leave that you know what you're doing.